of California, Davis. So Dr. Katerina joined the civil and environmental engineering at the University of Davis, California in August 2016. She received her PhD and MS degree in civil engineering from University of California, Davis, and did her undergraduate diploma degree in civil engineering from National Technical University of Athens, Greece. Her research focus on numerical and experimental studying ground failure due to earthquake liquefaction and mitigation. Based on her research, she has got the recognition in terms of recipient of the 2021 Arthur Casagrande Professional Development Award of ASC, American Society of Civil Engineering, the National Science Foundation Career Award, and the 2017 Greek International Women in Science Award. So now I request Dr. Katerina to share her screen and start the presentation.
Okay, hello from me. Good morning from California. Good evening, I guess, to India, and good day to all of you joining this presentation today. Let me quickly share my screen. Okay, can somebody confirm that you guys can see my full screen?
Yes.
It's perfect.
Okay, great. Okay, so hello, I'm Katerina Ziatopoulou. Thank you for the very nice introduction and of course the invitation to present today. I gotta say I'm very happy to be included. My research is not focusing directly on tailings, but I'm happy to be here today to show a few of our research cumulatively through the years that can be used potentially to address some of the issues that we are dealing with in tailing materials. So this presentation would not be possible without the group of people I have been working with through the years, Professor Boulanger out of UC Davis and graduate students Tyler Othis, Renmin Patel, and Francisco Humire, who have made very strong contributions to several aspects of this presentation. So before I go into the technicalities and the more of the outline of what I have decided to share with you today, I just want to take a step back and then discuss the utility of nonlinear deformation analysis as a useful tool in getting the responses of soils in the context of how they affect the broader infrastructure. So they're widely used in engineering practice to evaluate the static or seismic performance of geotechnical structures. And of particular interest for me today are those that pertain to sand-like soils that may liquefy, clay-like soils that may cyclically soften. And for those, in terms of models, we do have very limited options. And then we may also want to consider rate dependence during monotonic loading and slope stability applications, which is of a direct interest to tailings dams. In all of these types of simulations, the element level is represented by constitutive models, and I heard some of the mentionings from the earlier speakers regarding the utility of constitutive models, and one needs to understand that those are activated by specific loading paths as they're activated by the problem at hand. Of course, one also needs to understand that simulating a system level is basically the assembly of not only the constitutive model, but also the platform, the different choices, the site investigation data, and of course, the broader understanding that the analyst has of the problem at hand. Just to keep everyone on the same page, constitutive laws typically describe the stress-strain behavior of soils. They can be expressed in either total or effective stresses with, of course, different pros and cons depending on the application. And in the broader form, they will connect some stress increment with a strain increment or vice versa. Where in this D matrix here, as I have it, or tensor can be as complicated as the problem needs it to be. Now, of course, it is impossible to obtain closed form analytical solutions and incorporate all the constitutive models of soil behavior to satisfy all the fundamental requirements that we may have for the soils that we're looking at. So of particular interest and something to keep in mind as we are looking through the different types of models I will be talking today, we need to consider two aspects. The one is, of course, the necessity to have a theoretical framework that honors the mechanics of the targeted problem, but also a calibration. And it's usually convenient to see these as two separate procedures, of course, intimately connected, but still separate, that does tune the model to the broader set of targeted behaviors and aiming to be addressing the different types of operating conditions, if you'd like. So my presentation for today is going to briefly go over constitutive modelings of SANS for nonlinear deformation analysis. And in that context, I will focus on the broad range of behaviors we are setting our eyes on for SANS. I will talk a little bit about the PM4SANS model formulation and calibration. Then I will be spending some more time compared to the beginning to similar types of developments, but for plastic cells and clays, again, for the context of nonlinear deformation analysis. And then depending on time, I will discuss about a comparative calibration of PM4SAN and PM4SILT for the CATIA and TSF tailings materials against some available laboratory data. Openly available, of course. And then again, depending on time, I will be sharing some of our most recent work on constitutive modeling for silts with rate effects and some upcoming developments there. So I'll start first from PM4SAN, and before going into any details regarding that, I promise I will not show any equations. I will share plenty of material so that each attendee can take this study as deep as they desire. But the one thing I want to keep in mind today is what we know from our soils in the field. And in the most typical applications, the types of data we will receive are going to be SPTs, CPTs, shear wave velocity measurements, and then of course some index tests from the lab. And it's only in more needed or well-funded, I guess, applications where we will get some more site-specific laboratory information. Starting from these types of information, we then rely on the broader body of knowledge that we have on soil behaviors, which provide us empirical or semi-empirical correlations, and then, of course, typical responses about what to expect. Now, talking specifically about liquefaction and connecting now the types of properties we have with responses that we may want to keep our eyes on. We will be interested, of course, in triggering types of relationships, whichever one each one desires to use. Here I'm showing cyclic stress ratio versus equivalent clean sand corrected penetration resistance. We can see that also as a relative density x-axis. We may be interested in how the cyclic stress ratio varies with the number of cycles. That can be viewed as the effects of duration. Here in this plot, the different types of curves are different based on the relative density that they represent. We may be interested, and actually it may be necessary depending on the application, to honor the effects of overburden. Here, for those of you familiar with liquefaction triggering evaluations, captured as the K sigma factor, or equivalently the K alpha factor targeted at correcting our cyclic resistances for the effects of sloping ground, compared, of course, always to the baseline condition of a level ground. At the same time, we may be interested in how a shear modulus is softening throughout the increasing strain amplitude. We may be interested in the post-liquefaction volumetric strains that lead to post-liquefaction settlements. And of course, we should never forget the monotonic drained and undrained responses that are determining how our sands are going to behave. Now, taking all these types of responses into consideration, we need to consider that depending on the application we're looking at, we may have a high variation of the operating conditions. The operating conditions being having loose to dense zones, drain to undrained loading, depending, of course, on the scenarios, low to high confining stresses, particularly for dams, that can be really important, or we may have low to high initial static shear stresses. So ideally, if we want to have a model that is easily calibratable, usable, but it can also capture the broad range of responses, one needs to keep all of these in mind as we move towards such developments. I will briefly go into the formulation of PM4SAN now with some historic context and then a little bit of the things we're looking at. Now, in terms of history, we started developing it in 2010, and then moving to 2012 and 15, it got implemented as a dynamic link library for use in the platform FLAC. Now we have implementations performed by colleagues, of course, in Plaxis and in OpenSeas. We will be releasing soon version 4, and sometime within this year or next one, we're working on releasing a 3D version. And in all of these developments, they weren't just reformulations. All those developments were driven by this continuous validation against the different types of loading paths and that we run into practice, either from friends in industry or from researchers or from our own investigations. I'm going to touch on the framework, and I'm going to touch only on the aspects that are relevant to the remainder of my presentation. So as a framework, PM4CN follows the basic framework of the Dafali's and Manzari model, and as such, it's critical state compatible, stress ratio controlled, and it follows the framework of bounding surface plasticity. So first and foremost, discussing about critical state compatibility. Here on this plot, I'm showing relative density versus mean effective stress, the critical state line capturing the set of responses that correspond to the operation of large strains and this constant shearing under a constant stress that soils eventually reach as you shear them to large strains. The relative state parameter here captured as the distance of your relative density from the critical state line here through Bolton's empirical or semi-empirical relationship. And basically, we just need a metric to see how far away we are from the critical state line. And that's what the relative state parameter is exactly doing. And eventually, as you move towards the surface, the relative state parameter goes to 0, and the combined effects of packing through relative density or void ratio and overburden that have been found to be really important for sands can be very eloquently captured. The stress ratio controlled aspect of the model means nothing more other than honoring the basic and simplifying assumption that only changes in the stress ratio, here shown as deviatoric stress over the mean effective stress, can cause the necessary relative shearing and rolling of the grains that is, of course, macroscopically viewed as plastic shear and volume changes. Last but not least, the framework of the bounding surface plasticity. Here I'm showing the framework in the simplified QP space. So essentially here we have an, of course, exaggerated elastic cone in space capturing the elastic range of responses. The parameter M defines the radius of this elastic cone. And then, of course, the moment you exit this yielding cone, you start behaving plastically. We have 3 different lines here operating. The dilatancy line is separating the space between contractive behaviors if you're below it and dilative behaviors once you have crossed it. The bounding line is posing an upper limit to the stress ratios that the model can attain. And then, of course, the critical state line stays there as a function of the critical state friction angle. I want to note here that the model is operating in plane strain, at least for now, and we have removed the effect of loading angle. So the critical state friction angle is getting directly mapped to the critical state line. And then the other 2 lines are a function of the critical state line with 2 dials and then a function of the relative state parameter. What one can get out of these equations is that as you progressively shear your soil and your relative state parameter does go to 0, eventually these 2 lines are basically rotating as a pair of scissors in space before they eventually collapse on the critical state line. Now, the Faltin-Manzari model had a huge contribution to our ability to model, particularly the effects of liquefaction. And in that context, I would like to define the fabric tensor as the tool that gets us to that response. So if we consider a dense packing of idealized sand grains that are undergoing shearing, and I'm showing here 2 isolated grains, as we shear them, these grains are going to roll on top of each other, of course, experiencing what we call dilation, herein denoted as a negative plastic volumetric strain, at the same time associated with a plastic shear strain increment. The latency is defined in plane strain conditions. That's why I have this square root in the denominator here as the ratio of the plastic volumetric strain increment over the shear strain plastic increment in the denominator. What happens here is that as we're reversing our loading, and this is of particular importance when we're simulating earthquake loading effects, it is definitely easier, as we call it, for these particles to roll back down to their previous position before they shear back up again in the other direction. And this is experienced as an increased contractiveness. This increased contractiveness is what pushes points like B here on the bounding line to shed all the effective stresses they have and really contract deep down into the origin where we find these points A. And these are indicative triaxial cyclic triaxial testing from SANS. In PM4CN in particular, fabric, so let me go, sorry, one back. So the fabric was introduced as a tensor, basically as a metric of how much dilation are you getting as you're shearing your soils, such that later it can be used as an enhancer to the contractiveness. In PM4CN, in addition, we use the fabric tensor and a cumulative metric of it to facilitate the reduction of plastic modulus in hysteretic loops and facilitate better capturing of damping mechanisms. Now, of course, needless to say that the Fellas and Manzari does offer a great framework as the basis to model the effects of liquefaction because of all its features. What we did with PM4CN is we advanced the formulation and we did a generalized calibration at the equation level to improve the consistency with a broader body of experimental data and design correlations. So a few of the changes are listed here. Including the addition of the fabric history, the connection of plastic modulus, elastic modulus, and dilation to fabric and fabric history as it got added to the model. We did different constraints on the dilatancy to honor published relationships between peak friction angles and critical state friction angles, and everything was recast around the relative state parameter. Most importantly, and I will touch on that in a little bit in 2 slides from now, PM4CN was cast around 3 parameters addressing basically usability in practice. Now, the way we went about it was to prioritize the simulation of behaviors that are important to evaluating earthquake-induced liquefaction effects. And the 4 sets of responses that I want to emphasize here are cyclic mobility, the accumulation basically of strains after you trigger liquefaction, the cyclic strength, of course, and this basically becomes a matter of calibration, the behavior of dynamic modulus at damping throughout the various strain amplitudes, and then the ability of the model to honor drained and undrained strengths. Other important behaviors, as I showed before, are the post-liquefaction volumetric strains and the cyclically induced drained volumetric strains in dry sands. We placed an overall emphasis in providing a reasonable agreement to a broad set of design correlations. I will not go over these, at least for PM4CN. I have some for PM4SILT, but we have everything, drivers and manuals and sample applications on our website at UC Davis. Of particular importance that I talked about before in terms of usability is the casting of the model around 3 primary parameters commonly available from field information. The relative density can be estimated from SPTs or CPTs, and that will adjust the stress strain responses. The shear modulus coefficient, essentially a dial in the Gmax relationship, which can be calibrated either against in situ shear wave velocity data or any available correlations from the literature. And then in its most basic form, and when activating, of course, the 3 primary parameters, the HP naught coefficient, the contraction rate parameter needs to be calibrated iteratively to calibrate the cyclic resistance to the criterion that we want to use for our analysis. Of course, that range of all these behaviors that are pertinent to liquefaction can only be captured because we have 21 secondary parameters operating in the background. These have default values that can, of course, be changed if the user does have the knowledge and has exercised the model adequately, so that can be a more guided intervention, but also depending, of course, on what type of data you have available. So if you have more data, site-specific ones, then definitely more and more parameters can be calibrated. But for now, these have received default values from this exact generalized calibration that I talked about before. I will not show any comparisons for this model. All of those are available in the manual, but I will share so that you can at least get the philosophy from the PM4 model. So I've broken down the three parts of my presentation in some summative remarks. So for now, I just want to reiterate on the fact that PM4 is a critical state compatible, stress ratio controlled, bounding surface plasticity model that has been developed to approximate the range of behaviors important to geotechnical earthquake engineering practice. Now, the one thing is that the complexity that we have added was necessary to track the complex behaviors exhibited by liquefying sands. We talked about the three primary parameters addressing usability in practice. And then, of course, that's something that is not directly supported from the slides that I shared, but definitely the idea of knowing the responses that you're after and then deciding whether this is the right model to use, but whether you can actually get it to work for your application. I need to emphasize that for now, the implementation is limited to plane strain problems, so there's no 3D version yet. The formulation does not have a cap, meaning that you can only get elastic compression along a constant stress ratio K0 consolidation line. So you cannot use the model to capture any crushing or compression at large stresses, such as the ones you have at a cone tip or a pile tip. And as I already mentioned, we have removed the load angle dependency, essentially implying that the friction angle is exactly the same in extension, simple shear, and compression. Having gone over the background framework without too many details on the formulation, this was more going into capturing the philosophy of PM4 sand. I want to talk about PM4 silt now, which follows the philosophy, but it's targeted at different types of soils. So finishing up with PM4 sand, the need arose to have constitutive models that would be able to be used for clay-like soils, the types of soils that demonstrate stress history normalized behaviors. So, and in fact, we named the model PM4 silt, and I'm going to come back to that to avoid calling it PM4 clay. But the reality is that if you're interested in the dynamic aspects of clay response, then the model can be used there as well. Again, though, it's not usable in consolidation problems just because of the formulation. Now, I talked before about the types of behaviors that we're interested in for sands. So here, the types of behaviors that are of primary concern for seismic applications of clay-like soils are those that pertain to strength, whether viewed as undrained strength or normalized undrained strength. And then, of course, the cyclic strength, either the CRR, cyclic resistance ratio, or, of course, the cyclic shear stress normalized by the undrained shear strength. Of course, for earthquake applications, we are interested in the dynamic properties, whether those are viewed as the maximum shear modulus and how that degrades with increasing strain amplitude. Similar to before, but with a little bit more detail now. I showed earlier what we went after for sands and the types of behaviors we were interested in. Now for clays, we're interested, for example, in the monotonic undrained shear strength as a ratio, right? So that we have seen historically from numerous publications. It will vary with OCR, but in the way that we approach it is we do not specify an OCR, but we specify what we desire for an undrained strength ratio, such that the user can have a huge control over that. In terms of cyclic loading, and here I'm showing experimental results from Cloverdale clay, either as a stress strain loop on the top or as a stress path on the bottom, and we can consider these pretty much typical results. I have some others coming up next. And what we observe, for example, in a stress path type of plot is that those stress paths will shed a lot of effective stress, and they will go, say here, up to a pore pressure ratio of 80%. And this is something that we often see in silts and plastic clays, typically not going all the way to 100% RU. Non-plastic silts, on the other hand, they will more typically go to 100% RU. At the same time, from stress paths, we can observe that the moduli do not drop as low as they tend to do in liquefiable sands or non-plastic silts, and you get these fatter hysteresis loops, and you do get, you eat up more energy there. We still get this progressive accumulation of strengths. So we need to be able to get that basically. And this is these differences, but these also commonalities are something that drives the buildup of PM4 silt on the framework of PM4 sand. In my next slide, I also have some additional experimental data from Potrero Canyon, a former PhD student out of UC Davis. And we can see here for an increased plasticity index, we can see this, the more distinct fatter loops and the shedding of effective stresses, but not all the way to zero. And comparatively, for a similar material, but with a PI of 0, so non-plastic, we can see a behavior resembling that of sands. We are also after cyclic strength ratios, and what we see here is for clays and plastic silts in particular, one way to think about strengths is to take the strengths and then you take the cyclic stress and then you normalize it by the undrained strength, as I have here on the left and the right y-axis. Now, in this case, the issues have to do with the rate of loading that you expect to have in the field from earthquake and the rate of loading that you typically have in the lab. So for 1 Hertz, which is a typical reference shearing rate in the lab, your monotonic strengths from lab tests are going to be slower. So this plot is going to go above 1 for low numbers of cycles. So you can see it goes up to 1.3 or 1.4. As you go to higher numbers of cycles, so 10 to 40 in this mid-range here, you get about 80 to 100% of your SU, but that is about 60 to 70% of the strength at 1 Hertz. So to get the slope right, you have to bump up your monotonic strength to get the dynamic strengths right. In the model, we explain this by letting by getting the right slope. So this can be fit inherently from the model, and then get the slope also right and the strength. We have taken out rate effect. We have added them back up for PM4 silt R, but not now for seismic applications. Additionally, and something that is really well established for clay-like material, they of course the modulus reduction and the associated increase in damping as you progressively load a soil. Quickly going over the formulation, but with a little bit more detail compared to PM4 sand. We first developed PM4 silt in 2018. It inherits most of the features of PM4 sand, but it basically all the modifications will enable simulating the undrained monotonic and cyclic loading responses for low plasticity silts and clays. Similarly to PM4 sand, it is not intended for modeling consolidation problems with evolving strengths. And again, this is also limited to plane strain applications. The framework now has been a little bit changed, and I will show only the features that are of particular importance. So first of all, we have switched to a linear critical state line in the void ratio LNP space. Here, compressibility is captured with the slope lambda and the y-intercept gamma. Other than that, everything is the same as before. Now, the trick here, and one of the things that we have emphasized for providing ultimate power and selection ability to users, is to let the user choose the undrained strength. Of course, you put in a void ratio, you can specify the undrained strength. The undrained strength controls the mean effective stress, as I'm showing here, for example, in this illustrative plot at critical state. And that will anchor where the critical line has to be such that you can honor your targeted SU. So we're switching the calibration idea from not only inputting initial parameters and then letting the model tell us what the undrained strength is, but we have the model honor everything that the user knows about their material, such that can get reliably honored. So it's basically the undrained strength that needs to set the critical state line. The framework of the bounding, the latency and critical state lines remains the same as before, but now we don't have the relative state parameter anymore. We just have the state parameter, and other than that, the formulation regarding that stays the same. This is the view of the bounding and dilation stress ratio for a constant state parameter. In this next slide now, I'm showing the bounding surfaces for a constant void ratio. So here we have changed the bounding surface formulation, and we have separated for the wet on the right-hand side here. Please note the x-axis, that is a normalized mean effective stress over the critical state 1. So right at the intercept of 1, we are at critical state. So on the right side, we typically call this wet of critical, and on the left, we call it dry of critical. So in terms of the normalized shear stress, we have normalized P at critical state. On the wet side, right here, you can control where the bounding surface goes, and that will control your peak strength. That's when the bounding surface really kicks in. On the dry side, there's a different form of controlling that aspect of the response, and we get reasonable stress paths and cyclic loading. Now, the NB dry parameter, which is the dial that controls the location of the bounding surface, will not matter much unless you want your stress strain loops to really resemble lab data. The important thing to keep here is that the NB wet does control peak strengths, and I will show some example calibrations in a bit. Discussing a little bit about dilatancy and other aspects, we did modify the dilatancy to have a ratio of P prime relative to the minimum attainable P min value. So now we have locked in P min as a 1/8 of the critical state mean effective stress, but that can be adjusted. Other dependencies are the same as in PM4SAN, and this is exactly what I'm emphasizing here. Drawing parallel now philosophies from PM4SAN, and now we have 4 primary parameters, actually 3, depending on the type of application you want to have. The logic is exactly the same as in PM4SAN. You can do undrained shear strength ratio or an undrained shear strength. If you put it in both ways, then the undrained strength will win, and that's what's going to be implemented internally. This is not the peak strength. This is the strength at critical state, and it's important to note that. And here I'm showing, and I'm listing here potential pathways for specifying that type of value. The shear modulus is performing the exact same operation as in PM4SAN. It can get calibrated to in situ shear wave velocity measurements to anchor the maximum shear modulus. The contraction rate parameter can be used and calibrated to match the cyclic strength, and then the 4th parameter, this FSU that I have here, that can be basically, and this is optional, not optional if you want to do end of shaking type of calculations. But you can use that to degrade the strengths for the effects of cyclic remolding, sensitivity, or for that matter, changes in loading rate and in the post-earthquake stability. Okay, so such that you don't have to change models after you reach the end of shaking, which is something that is very typically performed. We're trying to keep one model throughout the whole simulation. Of course, similar to before, there's 20 secondary parameters, again, following the similar philosophy, and again, targeting of the types of responses that I set forward as priorities earlier. Now, I will show you what we mean by generalized calibration and how we try and get a range of behaviors that are reasonable compared to what we obtain in typical applications. Now, there's 2 aspects to this generalized calibration: the idea of modeling development, and that goes into back the history that I told you before, and how we constantly check and perform and receive feedback such that we can see if there's anything that needs to be adjusted or changed or advanced or reformulated. But it also targeting and demonstrating the functionality of the model and just giving a range of responses that will facilitate adoption in practice, which then of course will give feedback for model development. So everything goes kind of hand in hand. Now, here I have some indicative values for the types of things I will be showing. The manual and everything we have published on this model does contain a much broader sense of indicative responses. I will start first with monotonic undrained direct simple shear responses. Keep now in mind that all of these are single element simulations in FLAC in the implementation for FLAC 8.1, and the responses here are all with default parameters. So in this plots, I'm showing a stress strain stress strain response, and then a stress path for different strength ratios. So as you can see them here, 0.25, 0.5, and 0.75. Okay, and you can consider that that's 0.25 would be something like a normally consolidated clay, and a 0.75 would correspond to an OCR of 4, which goes back to me saying before that we do not have OCR as a direct input, but it is considered indirectly by the specified undrained strengths. At the same time, within each family of targeted undrained shear strength ratios, we have different values of overburden stresses. So what you can see here is that all, for example, simulations with 0.25 will go to the exact same critical state point, and so do the blue ones for 0.75, and so do the red ones for 0.5 undrained shear strength ratio. And then, of course, depending on which family you were in, from black to red and blue for 0.75, you can see the effect of overburden kind of increasing, but not quite a lot. Okay. Looking now at undrained DSS responses for different adjustments of peak strengths, and now I want to demonstrate the effect of this NB wet and the type of responses that we see here. I said before, NB wet can control the peak responses, so you can now progressively see that for 0.2 we get a higher peak strength, 0.5 an intermediate one, and then a 0.8, and then of course for an NB wet of 1 we end up having no dilatancy and then associated softening following that, but a direct monotonic increase straight to the critical state line. So what happens with a smaller NB wet is that the bounding surface plus bounding surface moves higher. The stress path can come up higher before it does hit the bounding surface. That happens right here, right? It will yield here, and then it will soften and go down to critical state, okay? And I just want to emphasize that all these now are all for a 0.25 undrained shear strength ratio and an overburden of 1 atmosphere. I want to quickly show what that post-shaking FSU factor is doing here. Again, everything that you see here is all run with a 0.25 undrained shear strength ratio, and then an overburden of 100 kPa. So what we do here in this driver is that we run the single element, and that's of course what would happen also in a system level analysis, all the way to 10%. And then we implement that factor, that FSU that I said before, between 0.8, the blue line, 0.5, the red line, and 0.2, the green line. And what happens is that you impose that strength factor, and you can change the strength that will operate after a specific shear strain threshold. And you can do that anytime you want, but the intention is that you do that post-shaking, and you account for the post-shaking effects of remolding, associated final softening, and so on and so forth. And these plots here demonstrate that utility. I'm going to look now at 2 illustrative responses from cyclic direct simple shear single element simulations for different types of conditions. So here, the left column is all stress strain loops, and the right column is all stress paths, all under an undrained shear strength of 0.25, normalized, of course, with overburden. And progressively, what happens between rows 1, 2, and 3 is that we increase the static shear stress ratio, basically increasing the sloping ground conditions on these types of elements. Now, so what we can see here is different types of things. Mainly, I want to draw your attention to the types and shapes of stress strain loops, the control of the excess pore pressure accumulation. This can be controlled by an internal parameter. It can or cannot get activated depending on the types of information you have. And then the progressive accumulation of strains as we are softening the soil. Similarly, for an SU ratio of 0.5, now this one is a little stronger. It has a lower excess pore pressure. It doesn't quite make it as close to the origin as the other one. And then as you increase your static shear stress ratio in rows 2 and 3, the model will accumulate more strains compared to before. Then it's going to be, and then it's even stronger, especially for an alpha of 0.2. And we can also try and compare that to indicative responses. I showed you those Cloverdale clay responses from before, or other indicative lab tests that we may have. Examining a little bit, and this is again the generalized calibration, giving illustrative responses of what the model will do with activation of the primary parameters and then minimal activation of everything else. Showing here the effects and the response with some default parameters for the effect of overburden. We have basically no effect of it for lower strength ratios. This is for 0.25. And then as we increase the undrained shear strength ratio, we do progressively get a dependence. The different curves here are for 1, 4, and 8 atmospheres. And this can be thought as going from loose sands to dense sands, and the less dependence, but you have less dependence here, but you still have some, not definitely as much as we have in sands, but still something to expect here. Last but not least, we want to see how the alpha, the static shear stress ratio, shown here for 0 level ground conditions, and then 0.1 and 0.2 increasingly changing the effects of sloping ground, again for 0.25, 0.5 undrained shear strength ratios, and then 0.75. And we can see here that and something that we knew from before, a static shear ratio can be detrimental for clays and low plasticity silts. I said earlier that we're interested in getting the modulus reduction and damping. Here I'm showing results only for a strength ratio of 0.25. And as a reference, I'm keeping my eyes on the well-established curves by Vucetich and Dobry from 1991 for plasticity indices of 0 and 15. And as you can see here, compared, of course, to sands, these do not show much of a dependence on overburden as we know from sands. And the model has been calibrated to honor these types of responses. And you can see the responses as the solid lines here. The dashed lines are the Vucetich and Dobry, and the dashed lines are the Vucetich and Dobry, and the continuous lines are the softening of shear modulus and the increase of damping that we get from the stress strain responses in drained cyclic direct simple shear testing. And of course, this is what the model will do at default. But if the user desires, for example, here I'm showing an indicative calibration for different H naughts. H naught is one of the secondary parameters that does control this aspect of the behavior. So if you have site-specific curves for the low plasticity silt or clay, then this is definitely something to activate and look at. My remarks for the PM4 silt section of this presentation, and as I enter my last part for today, PM4 silt was developed to provide improved modeling for low plasticity silts and clays for nonlinear deformation analysis. I want to emphasize there's no consolidation line. Going back now in time, that's why we didn't call it PM4 clay. But in fact, if you're interested in the dynamic responses of clay and those alone, then the model can definitely work, because those are going to exhibit stress history normalized behaviors. Now, the focus for PM4 silt was on seismic applications, and again, it doesn't model consolidation problems. It doesn't capture problems where you have evolution of strengths as you do a stage construction, and for soft clays or other types of similar soft materials. The calibration, again, depends on the available information, and that addresses the issue of usability and, of course, adoption. In its most basic form, it does need an undrained shear strength or an undrained shear strength ratio, a G max, your shear modulus at low strains, and then the HP naught, which will calibrate the strength. I showed you how the default values lead to the broader range of behaviors that, that you saw later. And of course, keep in mind that yes, you can adopt all of those to any site-specific data you may have. For the remainder of this presentation, and I do not think we're going to have time to go into PM4 silt art, but no problem. I just wanted to show a very sample calibration of both models actually for the Katia Northern Tailings Storage Facility out in Australia. So I think all of us will be familiar by this very impressive failure. Katia Operations is a mining and then processing complex located in New South Wales in Australia. It had a height of about 90 meters and it failed in 2018. Of course, fortunately and unfortunately, no major damage was caused by this failure, as the tailings were contained by the southern part of this complex as a tailings storage facility. This has been studied extensively by review boards and researchers and then practitioners, all published by Jeffries and et al. In 2019. And three of the speculated failure mechanisms were that either there was a progressive failure of the foundation materials, there was an excessive yielding due to pore water pressure buildup and raising and the associated increased pore water pressure, and then the pore water pressure buildup due to 2 magnitude 3 very minor earthquake events that occurred the day before this failure. Following this failure, lots of samples were collected and lab tests were conducted on the tailings and the foundation materials to investigate the mechanisms leading up to this failure. And after this event, we are now able to utilize in some of these data and evaluate the ability of the 2 models that I showed so far to simulate this behavior and see which one seems to be closer to the reality of the laboratory tests. So I'm going to go over a little bit the laboratory data and the indications that those gave for the soils operating in that site. The site investigation showed that the overall, we're talking about a fine soil, which has a high fines content between 55 and 65%, but definitely a low plasticity index. So it's not very plastic. The types of data available were odometer consolidation tests, shear wave velocity measurements from Bender elements inside those tests, and then monotonic and cyclic direct simple shear tests that were performed over a range of conditions, either overburden or sloping or static shear stress ratio conditions, to basically examine the range of responses that this material had to give. Looking now in the types of monotonic behaviors that we obtain here, again, I'm showing standard stress strain and stress path plots from the data by Jeffries et al. From 2019, and identifying the target behaviors, because what we're doing now is we're taking a step back and we're saying we don't know if this material is quite, it's going to behave as a silt or a sand, or at least preemptively. So we ought to take a look at the data and see what kind of responses seem to be operating, okay? So that we keep some relevance to the system level expected behavior. Now, these are results from an non-drain monotonic test, and this is conducted under 3 atmospheres, so quite a high overburden stress and level ground conditions. Now, the 3 main aspects to keep in mind here is the post-peak strength, and then the peak undrained shear strength, and of course the small shear strain stiffness. That is basically this slope here that is operating. Looking at example behaviors from the cyclic aspect of the response, and looking at the cyclic effects, whether that's liquefaction or cyclic softening remains to be seen. Now we're seeing results from undrained direct simple shear test. The criterion that was targeted as representing triggering was a single amplitude of 2.5% in one direction. These did have a little bit of a bias, an alpha of 0.05, and a quite low overburden stress of 50 kPa or 0.5 atmospheres. We can see different things here. The 2 most important things is a very strong accumulation of strains, a resemblance of the loops to those of a sand, a high shedding of overburden stresses, and of course, an associated very high increased excess pore pressure ratio. If we compare the two, and we can see that, first of all, we can see there is some dilatancy, especially in the cyclic testing. And, we can see that we can have a high accumulation of strains, but it is really hard to know which model to use and which model not to use, because both seem to be hinting that either PM4 silt or PM4 sand would be applicable. So what we did is we did indicative calibrations of both to see which one would be more applicable. So I'm going to go over this quickly, and then I'm going to wrap up. Now, for the calibration of the PM4 silt model, and following some very distinct steps, looking at how to honor the data that were available through the Jeffries et al. Report, there is the primary parameters here, I'm showing here at the top, and then the secondary parameters, and some of which we did activate because we did have a lot of data available. So first of all, we honored the measure parameters from monotonic DSS test. So this undrained shear strength approximately of 0.13 as we see here. Then for step two, we honor the critical state friction angle. So that's the angle that we considered as mobilized. Then from odometer consolidation tests, we anchored the compressibility and then the initial void ratio for this test. And then looking at published relationships and the relationship between Gmax, the dial G0, and NG, which is basically capturing the way that the modulus is changing with depth as we reach higher overburdens. Comparing that with maximum values of shear modulus that were published by the authors of the report, and reconciling the two, we ended up activating a 350 value for the shear modulus coefficient.
Dr.
5 more
Katerina,
minutes? Yes.
Yeah, sorry to interrupt, 10 more minutes.
What's that?
Yeah, sorry to interrupt you, 10 more minutes.
Absolutely, great. Thank you so much. And then the NG slope here basically anchored to what the authors considered appropriate for this type of material. Last but not least, for step 4 and 5, we did some single element simulations, monotonic ones, to see how PM4 silt with these parameters compares to the laboratory data. Of course, some refinements here can be performed, but overall, we consider the response quite satisfactory. And then that helps us also anchor the H0 parameter for the plastic modulus ratio. Now, last but not least, because we wanted to see both aspects of the response and how a monotonic calibration can end up leading to honoring the cyclic response. Here I'm showing the laboratory data that we had from the report. That's a stress path, and what we see here is we see a very high increase of excess pore pressure ratio, which means that we bumped up our RU max. This is one of the secondary parameters to 0.95, and trying to fix that aspect of the response. If we hadn't done that, the default value that PM4 silt allows for the model for the buildup of excess pore pressure to take place under is about 80 to 90%. So we changed that a little bit. Looking now at the cyclic strength and the strain criterion that was set forward by the researchers that published this data, we want to compare and anchor the HP0 calibration iteratively, of course. And here I'm showing comparisons of cyclic stress ratio versus number of cycles for a single amplitude of 2.5% between simulations and the laboratory. And this is not random. This had to do with this iterative variation of HP0. Looking now, taking another step back and seeing how PM4 silt performed against the data, we can see some discrepancies, but overall we could consider this as being a satisfactory match within reasonable engineering effort. for the monotonic responses. Comparatively, doing a similar calibration for PM4CN and with the types of information we had, it was nearly impossible to honor the peak strength, the softening of this response. So we consider that PM4 was more naturally capturing the behaviors shown by the data. At the same time, when we started looking at the cyclic responses and seeing PM4 and PM4CN and how each one would approximate the cyclic evidence from the lab. Here I'm showing again the laboratory on the left, PM4 in the middle, and PM4CN on the right. And we can see that because of its formulation and of course the way that it was calibrated, it is evidence that PM4CN does do a better job, particularly in the reduction of vertical effective stresses. As we can see here on the stress path, which was identified as one of the target behaviors here. Looking now on what we get on implied strengths from, and then Gmax, G over Gmax reduction with shear strain amplitude, keeping the Busetic and Dobry curves as a reference. The red curve is what we got before, and I showed this to you already from PM4 From PM4CN, we get slightly higher cyclic stress ratios, but still in the range implied by the laboratory. So one can consider those very satisfactory. And then, of course, PM4CN is also very consistent with the Busetic and Dobry curves, provided that those are going to be the ones of interest. We did some extra evaluations of comparing that against the EPRI curves for SANS, which do capture better the effects of overburden, and the calibration was again a very good match. Remarks for part 3, where I showed this comparative calibration of PM4 and PM4CN. Both were showing to reasonably capture, respectively, different types of responses. We will consider, however, that PM4 would be better used for a system level assessment of static liquefaction. So thinking a little bit of what kind of responses may be of interest. And we would probably suggest that PM4CN is used for the system level assessment of earthquake induced liquefaction. So it is up to the user to decide which mechanism needs to get emphasized. Now, of course, all of that is close, it's intimately related to the quality and the detail of the lab tests available. So, and then our ability to identify the target behaviors that are dominating the failure mechanisms. We have not done any system level evaluations yet, so this was more to emphasize what how calibration would look like, and how basically it's not only about just blindly saying this is the material you have and this is the model you need to use, but it's more about choosing the behavior and then letting the behavior choose the model for you. Now, I don't have time to go over some other slides that I have prepared. Just as a preview, I want to tell you that one thing we have coming up is the rate dependent PM4 version. The motivation for that was the undrained creep-based failure of the Feijiao Dam 1, documented by Robertson et al. In 2019. So basically looking at how can we do slope stability estimations, long-term stability estimations that may still take place in an undrained manner. Okay, so something that is coming up, it's still in beta testing. We will be sharing updates as they come. It is an extension of PM4 and we suggest that it's used with a creep module of FLAC. So that's what we're targeting at. It will come out within the next month or two, hopefully, so that I expect that will significantly advance our ability to simulate tailing storage facilities under undrained creep type of conditions. You can find more details in publications by Ross and Tyler, who have examined this at a system level. They already have 2 publications out from USSD and the Tailings and Mine Waste conference, and then our formulation manual will be released very soon. So with that, I will just want to reiterate the fact that I just shared with you a family of stress ratio-based critical state compatible bounding surface plasticity models. Our goal is to capture the range of responses between sands, clay-like soils in either seismic or slope stability applications. The philosophy is common across all of those, and it is addressing the idea to identify key behaviors. We have emphasized usability through primary parameters, and then generally I try to go over quickly the different types of things that we may be looking at, basically aiming with equipping you with some references so that you can perform your own investigations and satisfy your own intellectual curiosities. With that, I would like to thank you for having me. Professors Thafalius and Cutter out of UC Davis have been phenomenal and instrumental through all these years of different developments we have had. Different parts and pieces of this research has been funded from NSF and the Department of Water Resources. And here at the end, I have some condensed references where you can find lots of the work that we have performed through the years. And with that, I am done.
Thank you, Dr. Katerina. So now I'll request all the participants, those who have got a query, they can write in the chat box. In between, I have some queries. Should I go ahead, Dr. Katerina? Or you can also go through the chat box. So now, so let me start with one. So first is from Luis, that in the PM4 silt extension that is planned to account for viscous effect, would you consider that creep effects are acting the whole time? That is hypothesis B.
I'm not sure I know what hypothesis B is, but the way we have done the calibration for now and the way that the model has been extended and is being debugged, we are considering, let me scroll back up. We can consider, yeah, that creep effects are acting the whole time, or we can activate them after the static analysis or after the initial setup. So yeah, the intention was to get the creep effects across the whole simulation.
Okay, so now, no, these are all thanks. Okay, one more query. Okay, all thanks. There. Happy with the presentation. Let me, okay. So now from Juan Carlos, I was talking the time. Yeah, so can you go that I understand that testing with shear bias CDSS is a problem specific, but is there a specific alpha value that you would recommend on lab testing calibration? I'm thinking on tailing step.
My specialty and my experience is not on tailings material specifically, so I would refrain from specifying and telling you what alpha value to use for lab testing. From my own experience, at least from sands, I have seen that getting the effects of static shear stress ratios on cyclic strength is really important. So I'd like to see at least at 0.1 or a 0.2, just so that we can get a sense of the magnitude. One thing we have been doing over a project that I have with my colleague, Dr. DeYoung at UC Davis, is very systematically exploring the effects of static shear stress ratio. I find that the literature generally does not have many published charts. Of course, the empirical, semi-empirical correlations by Professors Boulanger and Idris have shown, the important tendencies, but we have found that those can be really, really sensitive to the triggering criteria we use, to the sample preparation method, to the protocol overall performed in the lab. So, and yeah, those are going much better into performance-based evaluations. So at least a 0.1 would be nice, but I don't want to say something on tailings in particular.
Okay, one more question again on the same tailings from Bob Bacchus. This is relation to that Brumadinho failure. And George also, Dr. George was also talking about this, that model failure of that new model and the Brumadinho. Do you think you can model the structural collapse mechanism that Brumadinho tailing dam failure?
So if I get this right, the question is if I can think we can capture the Brumadinho failure mechanism.
Yeah. I mean, with your model, can you that model that Brumadinho structural collapse? That's the question.
We haven't tried yet. I need to check with what Tyler is doing for the tail of his research. I'm not, very familiar with that failure, so that I know the specifics of the paths and the types of behaviors that were experienced there. If it's a matter of, a large run out, I don't know that we would be limited by the element level behavior or the ability of the flat grid overall to capture that. So that is usually something we experience as particularly limiting. So I hope, but again, for large deformations and large runouts, we may be limited by that before anything.
Well, your presentation has really created interest. Now, one more query. Great presentation. Do these models have room to take into consideration the material properties of any geosynthetic or composite materials for slope stability analysis?
My opinion is without having attempted something like that, my opinion is that you would have to take it more macroscopically into account. So if you wanted to consider the macroscopic effect of having such reinforcements on your soil, but they wouldn't be able to take the pull-out capacities or the tensile, either uniaxial or biaxial capacity of such, I guess, interfaces inside the broader body of a slope. So I wouldn't see that happening.
Okay, then nice presentation, great presentation. Okay. So I didn't find any more queries. I'm still voting.
Okay. So there's the one more question from the Johan. So it states that what plasticity index or what parameters would you use as a threshold in order to select a constitutive model over the other, that is PM for sand, PM for silt on tailings?
I'm not sure I followed. What is the plasticity index I would use?
That would you use as a threshold?
As a threshold. We don't have a threshold. That is the thing. We don't have plasticity indices or OCRs as inputs or as thresholds, basically emphasizing that, if you know how your model will behave, whether it has a plasticity index of 80 or 5, if you can calibrate the rest of the parameters to demonstrate the response that you think your material will have, then that is the intended use. But we don't have a range of applicable PIs. And in retrospect, this is something we don't regret. The plasticity index not being an input parameter, that was intentional. We do regret not giving a more appropriate name, to be honest. That will not make the model to be considered prohibitive for clay-like materials. So if you have an idea how your PI of 50, 60, 70 will behave, then you can calibrate against that. And your model is not going to distinguish between PIs necessarily, but it will distinguish between behaviors. I hope that, and that is one of the messages I really wanted to get across.
Okay, so I don't think any more query.
We have in some of the publications I showed earlier, we have one publication from Geo Shanghai. Then Ross has one publication with Professor Vijay Vikrame from UBC. We have done sample calibrations either from lab-based tests from a range of plasticity indices from 0 to 20 to 50 in the lab, and also from Fraser River silt. So you can see there how we approximate that, and how we get away from specifying a plasticity index, but emphasize the behavior. So there is lots of indicative calibrations there.
Okay, so I didn't find any queries so far. So thank you, Dr. Katerina. So
Thank
now
you.
we have come to end of the session for day 1. So it was all nice presentation by 3 of our speakers. Professor Torsten Wichmann, he started it nicely about the simple model of liquefaction, and he extended it to the reclamation of the lignite mines through which is done with the sand spreading. And then he was also talking about the parameters which governs the liquefaction potential of these reclaimed sites. We discussed it with also example, particularly Rhenish lignite mines in response to the earthquake of magnitude around 6. Thank you, Professor Torsten, to present a nice lecture. And the day begins with very good starting point. Then we have got the speaker, Dr. George Macedo. He talked about different mechanical properties of the mine tailing. He has got a good comparison of the data he presented. Then also pointed out important correlations required. And as also he was saying that the PI is more important than the clay fraction. And also he discussed about the different parameters for modeling and importance of that critical state soil mechanics model. So he emphasized that we should go with the critical state soil mechanics model. And then he also discussed with example of that Brumadinho failure, and then also told about the liquefaction potential with these mine tailings. Thank you, Dr. George. And at the end, we had Dr. Katerina, who discussed about that PM4 sand and PM4 silt model developed at University of Davis. She also, when we was talking about, you could have seen that she had discussed with the example, particularly that Cadilla Northern Tailing Storage Tailing Dam. So she also presented that the different applicability of that PM4 sand and PM4 silt model. They presented so many things to take home. So then also she discussed about the future models they are going to develop it. Based on that is the extension of which will be mostly strain controlled. So we had a good beginning on the first day of this international virtual short-term course. Hope for all the participants have enjoyed it. So I thank all the participants and hope to see you tomorrow. And I request all you join at 10:15 IST, which will be different time at different parts of the world. So I request all the participants to join at least 10 to 15 minutes before, so that we can start exactly at 10:30 AM IST. And tomorrow speaker is the first speaker is Professor Krishna Reddy. So we'll start in time. I request all of you to join at least 5 to 10 minutes before. Now I thank all the speakers of the today and also the participants. Thanks Professor Krishna Reddy for all the support, Dr. Lohit Kumar. And here we want to end the today's session. Thank you all.
Okay, sir. Thank you.